My name is Lucy Norval, and I am the coordinator of communications and programming for the Scarborough Public Library. And I want to welcome everybody tonight to Far Out, Distance on Astronomical Scales. And we've got our NASA Solar System Ambassador, Seth Lockman, here to speak with us about a pretty important topic. So Seth says that our brains cannot intuitively understand our own planet, let alone space. So tonight, we're going to do a cosmic zoom out of our solar system and cover different systems for measuring distance and how to develop an intuitive sense for each of them. And Seth is returning as our night sky tour guide for the Scarborough Public Library, and he has been volunteering for NASA as a solar system ambassador for a while. And we're really excited to have you back with us, Seth. Thank you very much for coming. And 2 nights in a row, last night you did a workshop on Mars and the rover that just landed, Perseverance, and that was really exciting. We might have a couple questions for you tonight about the rover. But just so you know, very, very quickly, I'll tell you a little bit about Seth. He grew up in down east Maine, and he developed an early fascination for the night sky. And he was guided by his father's love of astronomy, and he quickly learned how to use a telescope and different kinds of star charts. And then he went on to go to the Maine School of Science and Mathematics, and then he graduated from the University of Maine. And he works for a rocket company. And I'll let him tell you a little more about that. So without further ado, I want to welcome you, Seth. Thank you so much for coming. And we're excited to spend a little time thinking about what's far out.
Thanks, Lucy. I'm thrilled to be here. And it's true. I'm kind of a communications person as well for Blue Shift Aerospace based out of Brunswick, Maine. And a couple weeks ago, we conducted Maine's first commercial rocket launch, and it was really exciting to be a part of that. I can't talk about it too terribly much this evening just because I'm wearing my my NASA hat, but I'd be happy to maybe answer questions about that, or even to go in depth at another time, perhaps. Yeah, so I would love to just talk to folks about the sheer size of the solar system. We're not even going to look at the distances to other stars. We're just going to keep it in the solar system tonight and talk about how to contextualize and kind of get an intuitive sense for the distances and scales that we're measuring on just within our own solar system. Now, I do consider it a bit of a personal failure if I get through the presentation in the allotted time, because that means folks were not asking questions. So please, by all means, fire away. Feel free to ask a question, during the presentation. And if I don't catch it, Lucy will pass the question on.
Yeah, but we do have a question already. Someone's asking if they're muted. And the answer to that question is yes, because we are in a webinar mode so that Seth can share his screen. He's got a lot of really great images that he'll be talking about. So if you have a question, if you can type it into the chat, and if you can type it to everybody, then people won't ask the same one. Or you might see somebody's great question and that'll cause you to ask another question.
Sounds good. All right, so everybody on their screens should be able to see an image of the night sky. This is a simulation that I'm able to run on free software. And there are many phone apps and many softwares out there This one is unique because it actually will project a deformed image onto a curved mirror so that you could then reflect that out onto a planetarium dome. So you could use the software on essentially a dome-shaped screen, but it also works well on a flat screen. And so here we are looking out at the night sky at about 8:30. So it should be before everyone's bedtime this evening, I hope. But if right after this presentation you choose to go outside and look up at the night sky, this is a pretty good approximation of what you should see. Now, does anybody recognize any constellations just based on what we're looking at right here?
I don't see any answers coming in yet.
Oh, we're starting to get emojis.
Oh.
Orion, yes. Got a couple of Orions. Excellent. Yes. Now, oh, yes. Oh, very good. Yep, Taurus the Bull is also up here. So oftentimes when you go out into the night sky, you'll get a direction that you should be looking at, the north or the south. Well, in this case, we're looking south, but of course, most people's backyards do not have these helpful little letters carved out to, or lit in red just to let you know what direction you're looking at. So you have to start by finding a recognizable pattern in the night sky. And a number of people identified Orion, and here he is. This is Orion the Hunter. Right? There's his belt. He's got the 3 stars on his belt. He's got his sword, which is not 3 stars, it's 2 stars and a nebula. And then he's got his shoulder up here. We thought he was going to need a shoulder replacement for a little while. This star up here, Betelgeuse, got really, really dim about a year back. And now it's almost back to its full brightness. It turns out that it was a giant dust cloud that got spewed out of the star during essentially a really, really big solar flare. And then once that gas escaped the star, then it blocked out the light from the star as seen from Earth. And then down here, this is Rigel in his ankle. We'll come back to that star in a moment. So Orion, it's pretty easy to see a guy, right? Like there's his legs, there's his belt, there's his shoulders, right? So you can see like kind of his torso, right? But it can get a little tricky to see what the ancient Greeks were seeing in the night sky. Like for example, if I tell you over in this chunk of the night sky right here, if I told you there was a dog, how many people can see a dog here? Well, let me help. There we go. So this is an artist's kind of rendering of some of these images here. So now you can see Orion, right? He's got his club up here. Sometimes he's depicted as holding a shield, sometimes a lion skin. You can see his sword there, right, in his ankles. And you can see that there are many, many other constellations laid out across the sky. Someone mentioned Taurus, right? There's the V of Taurus the bull's head. And here's Taurus the bull. Now, here's a fun fact. When an astronomer says a constellation, they're not necessarily referring to what is being depicted here in the night sky. Or maybe you've seen a map that looks kind of like this here, with the lines connecting the stars, right? So what you have here is called an asterism. So this star pattern that we're seeing here or here, right? That's the asterism. The constellation is actually a region of the night sky, kind of like a country in the sky. And so Orion, the asterism, is here. Orion, the constellation, kind of goes here, and it's got a border with the rabbit down here, and then it comes up around here. And so the constellation is the region, the asterism is the pattern inside it, which is how you can say things like the moon is in Taurus, or because the moon isn't actually inside. Actually, it just about is inside the shape of the asterism of Taurus, but it's also within the region. It's within this border of space. Or Mars, technically right now, is in Aries. So this drawing actually strays a little bit outside the border where Taurus ends and Aries, the ram, begins. So the feature that I want to show you tonight is called the Winter Hexagon. Let's see if we can pull this down. And we're going to start up here in this kind of pentagon. See how it looks kind of like a house leaning off to one side a little bit? Well, this is Capella. This is the brightest star in this little asterism, which is called Auriga. And we're going to go around some of the brightest stars in this region of the night sky. So from Capella, we're going to go down to Aldebaran. This is the eye star in Taurus the bull. You may recall. See, Aldebaran is right where his eye is. He's very angry. That's why his eye is red, anger. From Aldebaran, we go down to Rigel, right? And that's in Orion's ankle. We're going to go up to Sirius. And this is the head star of the bigger of Orion's two hunting dogs. And we're going to go up to Procyon in the smaller dog. This is the tail star of Procyon. So you see that's kind of on the back end of the dog there, but there's Sirius, there's Procyon. From Procyon, we're going to go up here. Now, did you saw the picture of the two people? They're maybe brothers. Does that ring a bell as to what constellation that might be? Well, it's Gemini, right? Yeah. Liz got it. Those are the Gemini twins, Castor and Pollux. And in fact, there's Pollux the star, and there's Castor the star. So is Gemini one asterism or two asterisms? Who knows, but it's all one constellation. Whoopsie. Once you get kind of high up in the night sky, the movement gets a little weird. Anyway, from Pollux, we draw a line back to Capella, and that completes the hexagon. We have the 6 stars: Capella, Aldebaran, Rigel, Sirius, Procyon, and Pollux, and then back to Capella. Now, if that's a bit much to remember, because I certainly could not do it, there's what we call a mnemonic device, where you make a sentence out of words that begin with the same letters as whatever it is you need to remember. For example, instead of Capella, Aldebaran, Rigel, Sirius, Procyon, Pollux, you could say, Captain, all the rigging seems properly polished. Huh? So Capella, Captain, Aldebaran, all the Rigel, rigging, Sirius, seems, Procyon, properly, Pollux, polished. Captain, all the rigging seems properly polished. Got it, everyone? And that is the Winter Hexagon, 6 of the brightest stars up in the winter sky, in kind of the southern half of the sky. But you don't need to know that you're facing south. You just kind of turn around until you see Orion. And there you are at the beautiful Winter Hexagon. If you draw a line between these 2 stars here in Orion and just go kind of perpendicular to them, you'll wind up at Capella, and then you can start with the mnemonic device.
Seth, if people want to take a look at this planetarium software that's free at home, how do they find it? What's the name of it?
Yeah, so the name of this particular software is Stellarium. Stellarium. And
So
sorry?
they could just Google Stellarium and get the software. Okay, great.
Yes. Yes, and there are many apps like it. There are even apps that you can download on your phone that will take your phone's accelerometer. And so you can point your phone up at different stars and it'll tell you what you're looking at. And you want to be careful with that because the light from your phone can damage your night vision. It's nothing permanent. It's nothing dangerous. It will just mean that your eye will take about 2 hours to adapt to the darkness of the night sky and really get all of the detail and all of the light that you can get from the night sky. But if you're just getting started, those types of apps are a really terrific way to just bring that information with you, and just you can look right past your phone up at the night sky and see what's being depicted, and it can be a really great way to begin developing that sense as you start looking at the night sky. If you want to come back indoors and see a higher detailed version of what you were looking at and maybe get to zoom in, and as you can see here, you can get some really terrific information on the celestial bodies, the moon, the stars, the other planets. Then Stellarium, can be pretty good, or programs like it. And you can also see what things will look like in the future, thousands of years if you want, or you can just kind of speed things up and you can see Orion chasing Taurus across the night sky, followed by his 2 hunting dogs, Canis Major and Minor, locked in their perpetual chase. And so that's part of how the ancient Greeks would tell stories, is that before TV, the moving sky would help to tell some of the stories. And if the sky looks like this tonight, you're probably up past your bedtime. All right. And now for our feature presentation. Oh, come on. Any second now. Full screen. Laser pointer at the ready. Whoopsie. So as Lucy mentioned, today we are going to talk about distances. Really mind-bogglingly big distances, because space is huge. If you think it's a long way to Grandma's house, space is much bigger than that, because the distance between your house and Grandma's house is in space. Really big. Here's an exercise to kind of help dial in that cosmic perspective and start to step outside your normal sense of the world, which is really useful in your day-to-day. But sometimes you have to kind of step outside of it to start understanding the universe. So here we have a beautiful picture, right? This is the skyline of Barcelona, Spain. Beautiful city. So I hear. I've never been there. I'm going to put a question to you. What time is it in this image? Doesn't have to be specific. There's some margins of error here. Roughly, what time would you say it is in this image? Excellent. Virginia says night. That's correct. There are some other guesses here, more specific. But it sounds like we're looking at kind of like the late evening, or sorry, late afternoon, early evening, right? Kind of dusk. Well, asking for a precise time would be a little bit of a trick question because this is a long exposure, which is how you get this kind of halo around some of the city lights. How you get some of this movement here from these are car lights, headlights and taillights moving through the city. But generally, yeah, you could definitely say this is the evening or this is night here in beautiful Barcelona. Except 8:30 p.m. That's a good guess, Liz. It's a little later. That's good, you know. Kind of space out our guesses. That's good. I like to see some dissent within the group because that usually invites discussion, which we can't really do fully through virtual. But I'm loving these guesses. So what would you say if I told you it was daytime in this image? You think like, oh, he's crazy, right? I just signed up for an hour with the crazy person, right? But seriously, think about it. Where is it daytime in this picture? Ooh, is that the sun? Excellent question. No, it is not the sun. But you're getting warmer. You're getting warmer to what I'm hinting at here. It's daytime in Maine. Indeed, it would. Also getting warmer. That just because in some parts of this image here, it is night, certainly in other parts of the universe, at the time or times that this image was taken, it could be day. And we have our answer, moon. Indeed, we have the moon here fully illuminated. Now, the moon is reflecting light from the sun, right? And so if you were standing anywhere on this line on the moon, well, it's actually a little bit more like that. But if you were standing on this line of longitude, it would be noon. The sun would be directly overhead. If you were to look up, which of course one should never look directly at the sun. But anywhere on this entire half of the moon, if you were there, you would be experiencing daylight, daytime, and you would be looking up, and this part of the world would be dark with little specks of light across it, nightlights of the cities. So here, it is very much late evening or night, perhaps, but here, it's daytime. Here, it's noontime daytime. So the way we experience time is kind of an approximation of how we experience movement through space, right? Time is a place. This concept is utterly useless in your day-to-day. However, when you start thinking on these grander scales, these delineations we have, these concepts we have that have very little overlap, they start to kind of shift and blur together. And you can experience the universe in a very different way at these larger scales. This is just one example. All right. And that's not supposed to happen. Here we go. Okay, so let's talk about scales of distance. Now, this first question is going to be a little bit hypothetical. How far would you have traveled were we all at the Scarborough Public Library tonight? And everybody's probably going to have a slightly different answer. Right? Here's the Scarborough Public Library. Give me my laser pointer. And you can kind of zoom out in rings of distance, right? A couple miles up here to the main mall. It's about 15 minutes to get just a up in this general area. I actually lived up here for a little while. So maybe some people live right nearby, right? They walk 1 block and they get there. How far is a block really? Well, it depends on which city you're in, how they define a block. And even an individual city can have different types of blocks. So it's a good shorthand, but it's not the most precise measurement, right? How about a mile? Now there's a precise measurement. A mile, that can be a pretty easy unit of distance to comprehend. If you've ever had to run a mile, a very unpleasant experience, I say. You know about how long it is, right? At a light jog, a mile is about 3 songs. But a song is kind of a unit of time, right? So let's say you took like 10 or 15 minutes to get to the library. I have got to get rid of that bird clock. I apologize, it's not a bird, it's a bird clock. So if you say it takes me 15 minutes to get to the library, well, that could mean a lot of things. 15 minutes could be 1 block if you're walking, right? But if you're driving, 15 minutes could mean that you're coming from South Portland, right? It could mean that you're coming a great distance off of the interstate. And depending on your flight trajectory, whether that's ballistic, like you got shot out of a cannon at the circus, or whether maybe you had a parasail, you know, and you glided into the library, or maybe you landed at Portland Jetport and then took a cab, right? There are different types of flying, all at very, very different speeds. So to say, oh yeah, I traveled 15 minutes, well, that gives you some sense, but it's just an example. On even in our day-to-day, sometimes we'll use time and distance interchangeably, right? Now, just dealing with distance yourself, one fun exercise is to come up with a unit based on yourself, right? So, for example, I am about 5 feet 11 inches, rounding down slightly. That's my height, 5 feet 11 inches. Well, who gets to define the inch? Actually, the United States government. But so long as I'm not, you know, using these units to try and like sell anything, I can make up my own units. So we're going to convert from the US standard system over to the Seth system, right? So 5 feet and 11 inches is now 1 Seth. So to get to this presentation, I traveled about 18 feet and 7 inches. I measured the distance from my kitchen to this desk where I am now, which is about pi Seths. That's about 3, just a little over 3 times my height if I was standing up. And you can do this too. Once you know your height in US units, you can figure out all kinds of distances using your own height. And if there are any kids in our audience, as you grow, you will notice that your unit counts for more and more units in the United States standard system there. So that can be really fun. Okay, so I think we've laid a little bit of groundwork. Let's talk about how big the planet is, right? Will you stop stopping? Thank you. How big is the Earth? Well, the Earth is about 8,000 miles from side to side as the crow flies. Of course, that's assuming that the crow can fly straight through the Earth's molten iron core, which is not very realistic. So let's just kind of assume that there was like a road going around the Earth's equator or circumference, right? I guess you'd have to build a bridge over the Indian and Atlantic and then Pacific Oceans. So if you were to drive in a circle around the Earth, it would be about 25,000 miles. Now, 1 mile you can imagine, maybe 10 miles you can imagine. Anybody who's ever run a marathon, I guess you can imagine just shy of 30 miles. 25,000 miles. That's a bit much to wrap your head around, right? So how else can we define that? Well, based on Manhattan blocks, or a city block in New York City, downtown New York City, it'd be about 150,000 blocks. And that's a very long walk, even for somebody from New York. So let's try another way. How long would it take you to drive this distance? Well, we're going to assume that cars travel at 60 miles an hour. Now, I know that really cars travel at closer to 80 miles an hour, but we're just going to assume 60 because that makes the math a little bit simpler. So 25,000 miles divided by 60 miles per hour gets you 415 hours. 415 hours, that's a lot of hours. That's also kind of hard to contextualize, right? It's also kind of hard to understand what that means just based on the numbers. So we divide by 24 and we get the number of days. 17 car days. So that's a little over, that's like 2.5 weeks in the car. Assuming the car never breaks down, you never have to stop for gas, you never have to stop to sleep, and you never have to stop to get out and take stretch breaks. You could drive all the way around, assuming that there was a road, again, you drive all the way around the world in about 2.5 weeks at safe highway speeds. Okay, so how far is the moon? How far can it be, really, right? Well, it turns out pretty far. Now, we immediately run into a problem. See, we've been to the moon before with the Apollo program, and we're going to be going again pretty soon with Artemis, which I'm definitely looking forward to. Now, each Apollo mission took a different amount of time to get to the moon, depending on where the moon was in its orbit when the spacecraft launched. But it was always between 55 and 76 hours. So how much time is that? That's a little over 2 to just a little over 3 days. Earth days, of course, because the different planets rotate at different speeds, meaning that a day on each planet is different. So we're going to say it's 2 to 3 Earth days, right? So does that then mean that this spacecraft here was traveling at a constant speed similar to what a car can do on a highway? Well, no. No, because in space, things are a little bit different. A car going down the highway has to fight air resistance, and it also has to be controllable the entire time. In space, when there's no air resistance, controllability changes a little bit. And so you're not really limited by speed in the sense of your ability to maybe spot something down the road and then stop or change direction to avoid it, right? So when the Apollo spacecraft left for the moon, it would fire its engines right about here, and it would be going about 26,000 miles an hour. And as it would climb higher and higher, farther and farther away from the Earth, it would slow down and slow down until it crossed over to a point in space where the moon is kind of pulling on it more than the Earth is. So we say it's crossed into the moon's sphere of influence. At that point, it's traveling about 2,000 miles an hour. So it's not traveling at the same speed the entire time. And then once it starts falling towards the moon, it starts speeding up again, and then it hits orbit. And by that time, actually, well, it has to fire its engine to slow down into orbit. And then it's traveling about 5,000 miles an hour once it hits orbit. So with a little bit of calculus, some very advanced math and everything, you can kind of work backwards and figure the moon is about 234,000 miles away. And you have, that math is so complex because it's impossible to really send something towards the moon at a constant velocity, or at least solid objects. So it turns out that there is something that travels at a constant velocity, like almost always with very, very little error, and that is light. Now, the speed of light is about 670 million miles an hour, or 186,000 miles per second. It goes, if light was traveling around the world like that car, in 1 second, it could go around the world 7.5 times. That's how fast, that's how incredibly fast light is. And constant. Light doesn't really speed up or slow down, assuming that it's traveling through the same thing. So light in a vacuum travels a little bit faster than light through glass or light through air, but we'll worry about that later. We're just talking about the speed of light. We mean light through space. Excuse me. So the folks that set up Apollo, they knew that. So they thought, what if we put a special mirror on the moon and then we shot a laser at the moon and we timed how long it took the laser to go from the laser gun, essentially a laser gun, to the moon and then bounce back and then hit a radar dish. And based on that time, you divide it by 2. And if we know the constant speed of light that entire journey, then we should have a good, reliable distance to the moon. And so what they found was that when they fire the laser, they would detect that same laser back on Earth about 2.5 seconds later. And so what that means is that the moon is about 1.3 light seconds away. And we've been able to dial in that number very, very accurately to just give or take a few centimeters over the years. We know that, oh, yeah, let me also say, it's about 250,000 miles, 226 to 52,000 miles away, depending on where the moon is in its orbit. It's not a perfectly circular orbit, so it may be closer or farther from the Earth at any given moment, which is why our tides are not always the exact same. When the moon is closer to the Earth, it attracts the Earth and the Earth attracts the moon a little bit stronger than when the moon is farther away. And as a result, when the moon is closer, you're going to get higher high tides and lower low tides than when the moon is farther away. We also know from these measurements that the moon is getting about 1.5 inches farther away from us every year. And it's been doing that for millions and millions of years. So when dinosaurs were around, the moon was much, much bigger. And it's going to continue getting smaller and smaller over time until eventually, if we don't do anything, it's just going to kind of drift off into space and escape completely. But that's hundreds of millions, if not billions of years away. We don't have to worry about that. But if you're like 10 years old, the moon is about a little over a foot farther away. Actually, no, if you're 8, the moon is about a foot farther away than when you were born. It's kind of weird, huh? So if you could drive around the Earth, right, that's 17 days, you'd have to do that 9 additional times to drive the distance to the moon. So it'd be about 170 days to drive there by car at 60 miles an hour. Kids, now you can understand why your parents tend to drive a little fast, right? And if you were just dealing with the Earth's diameter, then you could fit about 30 Earths between the Earth and the moon. So 30 diameters, 10 circumferences, 170 days. That is a very long car trip. That is months in the car. Okay, let's zoom out a little bit farther and talk about distance to the sun. How far is the sun? Now, 170 days, let's see here. That's almost 6 months. So you could get to the moon in a car in about the same amount of time that it would take you to get to Mars with a spaceship. So cars really aren't that fast on a cosmic scale. It would take you much longer, much longer to drive to the sun, and you would need a very powerful air conditioner, so I would not advise it. Let's talk about how far the sun is, though, because at this point, it gets so big that miles stop making sense. So we invented a new unit of measurement. It's a little bit of a cop-out, but an astronomical unit is the distance between Earth and the sun. So how far is Earth from the sun? Well, 1 astronomical unit. Well, how far is 1 astronomical unit, though? We really, to say it's 1 Earth-sun distance, that's a tautology. That doesn't really convey any useful information. So let's define an astronomical unit in terms of a different scale, right? Well, if you do some fancy math and you look at where Venus is relative to the sun as viewed from Earth, and you do some triangulation and some SOHCAHTOA trigonometry, basically you get an answer, depending on the time of year, of about 91 to just under 95 million miles. Again, Earth's orbit is not perfectly circular. It's nearly circular, not perfect. And actually, it's one of the reasons that we in the Northern Hemisphere, it may not feel like this right now, but we actually have the more temperate winters, because the Earth is a couple million miles closer to the sun when our hemisphere is tilted away from the sun. And so our winters are not quite as cold as those in the Southern Hemisphere just because of that. This is a depiction over here of the Goldilocks zone. So in this green zone, you can have stable liquid water on the surface of a planet. This far away from the sun, you would have just ice, kind of like on Mars. We know that there's water ice on Mars, but liquid water is very, very rare because it's just too cold. And closer in, like on Venus, you might have some water vapor in the clouds on a good day, but there's no stable liquid water on the surface because it is just too hot. And so you need a planet that's just about the right distance from its parent star to support a full water cycle. So you have frozen water up near the poles, you've got vapor water in the air and liquid water on the surface, and a complete water cycle. That's what they call the habitable zone. It depends on the energy output of your star where that habitable zone is going to be. And that doesn't really tie into this whole presentation, but I thought this was a nice picture, so I used it here, although it is unrealistic to put Jupiter this close to the sun. But this is just to demonstrate the concept of what a habitable or Goldilocks zone is. Good Goldilocks because it's just right, like that third bowl of porridge. But this distance, in addition to being a kind of a Goldilocks distance for Earth, thankfully, this is about 1 astronomical unit, or about 93 million miles, or if you wanted to be a little more precise, 91 to 94.5 million miles. We already mentioned that we found this distance by measuring, where Jupiter is here. Normally that would be the planet Venus. And we can measure its, if it was over here in its orbit, you would have kind of a right angle made by the planet Venus relative to these two lines that you draw, and then you can work backwards and calculate how long this distance is based on these angles. So 93 million miles is about 400 times the distance from the Earth to the moon. So you could say 1 astronomical unit is 400 lunar units if you wanted to. At these distances, also, sometimes it makes sense to start measuring things in light time, right? So the moon is about 1.3 light seconds away, right? Well, the sun, working again from this figure that we get by measuring the distance between Venus and the sun relative to the distance to Earth, we can guess that it would take light about 8 minutes and 19 seconds to get from the surface of the sun to the surface of the Earth. Now, this is very difficult to verify experimentally because you cannot really land on the sun and put a giant laser retroreflector there in order to bounce light off of the sun. So this number really has to be arrived at by very, very carefully calculating that separation, the angular separation of Venus. But there are other ways to do it too. Like you can calculate the sun's energy output based on its brightness and mass. And then you can try and calculate how much of that energy is hitting the surface of the Earth. And that should be roughly consistent with that distance you calculated by looking at Venus, and it is. So there are many, many different ways to come up with an approximate measurement. And every system we've come up with has supported that about 93 million mile distance, which means that it's about 8 minutes and 19 light seconds away. So if the sun just went out, right, if it just stopped shining, we wouldn't know about it for almost 8.5 minutes. Ooh, good question. Would it take about 2,400 months to drive around the sun? I don't know. I'm guessing that you did the math. Maybe if we have a little time later, I'll walk through the exercise with you guys. So here's a fun thought. If it takes light 8.5 minutes to get from here to here, how long would it take sound? Now, of course, in space, there's no air. Air is what conducts sound. So sound could not travel from the sun to the Earth. But if it could, how long would it take? Well, let's take a look at lightning to get kind of a clue. So how many people know this trick? You go out on your back porch in a lightning storm. Hopefully your porch is kind of protected, and you wait for the lightning bolt, and then you count 1 Mississippi, 2 Mississippi. And if you count all the way to 5, from seeing the flash to hearing the bang, then you know that the lightning is about 1 mile away. So does that mean that light travels 5 times faster than sound? And I got trapped into that first time I tried this thought experiment. And no, because that's assuming that the light takes 1 second to travel from the lightning to you. But actually, you perceive the lightning almost instantaneously. The light travels over that mile-long distance in much, much less than 1 second. And then it takes sound 5. So it's not a 5-to-1 ratio. It's a 5 to almost 0 ratio, but not quite 0. Right? It takes just a tiny amount of time for that light to reach you. So we know that through other experiments, we've determined that the speed of light in a vacuum, of course, is about 670 million miles an hour. And we know that the speed of sound is about 767 miles an hour, or about 1/5 of a mile per second. So if you take those two numbers and work out the quotient there, light is about 874,000 times faster than sound. Now that doesn't mean much on its own, but we can take that and work backwards. If it takes 8.3 light minutes, 8 light minutes and 19 light seconds, right, for light to get from the sun to the Earth, all you have to do is multiply that figure by the 874,000, and you get 14 years. So if you could hear the noise coming off of the surface of the sun, which is an ongoing nuclear reaction, so that would be very loud, you would be seeing the sun, if you could look at it safely through Weldon glass, you'd be seeing the sun from a little over 8 minutes ago, but you'd be hearing the sun from about 14 years ago. So if you're younger than 14, the sound waves that were generated by the nuclear activity on the sun, if they could propagate through space, which they can't, but if they could, if you're younger than 14, they wouldn't have arrived at Earth yet. Now, interestingly, the sound itself would be about as loud as 120 decibels. So if you were on the surface of the Earth and sound could travel through space, the sun would be just this constant loud explosion at about the volume of a rock concert, which would be very distracting. And I'm so glad that sound cannot travel through a vacuum. Okay, let's zoom out even a little bit more. How big is the solar system? Now, this is a really interesting question because we don't know. So let's work backwards and redefine the question a little bit. Where does the solar system end? Now, this is a little bit easier to answer because there are a couple of different regions that you pass through that are pretty well defined as you head out into interstellar space. So this here is the Oort cloud. This is essentially a giant asteroid belt. So you may know that between Mars and Jupiter here, there is a belt of asteroids. It's not like in the movies at all. If you were standing on one asteroid in the asteroid belt, you would not be able to see any other asteroids in the asteroid belt. They're all so far apart that the human eye wouldn't even notice if you were in the middle of the thickest part of the belt. However, there are more asteroids in this region of space than, in this region of space or that region of space. So we call it the asteroid belt. It's not really a ring. It's not really close enough to that you could see it as an object like the rings of Saturn. So it's a belt. Well, when you get out to the Oort cloud, it's even less compact. It's even more spread out than the asteroid belt. So we call it a cloud, the Oort cloud. And it's very, very spaced out, but there's a lot of stuff out here. We don't know exactly how much stuff because we're talking about these very, even if you had a rock out there that was the size of a planet, like the size of Pluto, there's very little of the sun's light out here to reflect. So it's very difficult to detect objects in the Oort cloud. But we do think that early on in the solar system's history, a number of objects in the Oort cloud did get dislodged somehow and kind of slung by gravity further into the solar system, because out here things are moving so slowly that a tiny, tiny change in speed can really shift your orbit. And so sometimes objects from the Oort cloud, they go kind of screaming into the inner solar system. And that's where we get most of our comets. Our really long period comets are probably icy asteroids. They're so cold out here that water ice is basically like rock. It's so cold that there's no slipperiness, right? Water ice is the same out here as granite would be to us, like at our temperatures. And so it gets closer into the sun, and then all of a sudden it's got all this heat energy coming in from the sun, and it grows a tail as the water kind of diffuses off of it. Actually, comets have two tails, one of that water ice vapor, and then another of dust and gas that kind of it's heavier, so it gets separated from the water ice tail. So that's where many comets come from. Because it's so hard to detect these objects when they're all the way out here, we don't really know how many there are, and we certainly don't know where the edge is. We know that it's somewhere between 1 and 3 light years, roughly. So from Earth, it takes about 8 minutes and 20 seconds to get to the sun, traveling at the speed of light, right? So this, 8 minutes, and then a little bit. From here to here is like a year traveling at the speed of light, which is so fast that we can't travel that fast. We would never, ever get out here in just a year, not without some really amazing kind of sci-fi, warp drive, phaser-matic kind of special engines. Now, depending on our estimate of where the outer limit of the Oort cloud is, where things are still orbiting the sun, no matter how far away they are, they're still going in a circle, and they go so slowly, it could take millions of years this far out, or hundreds of thousands of years this far out to go around even once. But it could extend far enough out that in about 33,000 years, this star here, Ross 248, is going to get inside the Oort cloud. It's entirely possible, depending on where it ends. So for a while, there could be 2 stars in our solar system. Isn't that kind of crazy? But that one wouldn't really be gravitationally bound. It would just be passing on through. So let's move in a little bit closer, because we don't really know. I mean, we have a pretty good idea of where this starts. We really don't know where it ends. So yeah, moving in, I saw a question. Let's talk about the termination shock and the heliopause. So the sun has a solar wind. Do you remember earlier we talked about Betelgeuse, that star in Orion that pushed out this giant cloud of gas? Well, it's usually not quite that gassy, but stars are basically doing that all the time. And our own star, our own sun, has a solar wind, and particles that are kind of the result of all of that nuclear activity on the surface, they're getting flung out at 1/3, 2/3 the speed of light in some cases. And so they hurtle throughout the solar system. There are electric charges on them, which helps to keep the solar system clear of all kinds of really highly energetic rays coming from black holes and neutron stars and all kinds of things. So the solar wind, the sun might give you a sunburn, but that is better than getting a burn from galactic or cosmic intergalactic rays. So the sun's solar wind and all of its radiation creates this kind of a pressure bubble. And to be clear, this is a vacuum over here, this is a vacuum over there. So these are very, very tiny, tiny differences that a human would never be able to perceive. When I say pressure or wind, this is not pressure or wind like we humans experience it at all. But the solar wind blows out, and it goes out to this termination shock. And this is where the interstellar medium, or the gas of interstellar space, kind of gets parted by this constant stream of wind from the sun. And so that region on the sunward side is called the termination shock, and then on the spaceward side is called the Heliosheath. And the Heliosheath is this really interesting region of particles interacting. And so you have the solar wind essentially slowing down as it starts to hit resistance. It starts to interact with something other than other solar wind particles headed in roughly the same direction. And so this region of space actually heats up quite a bit. But because it's basically a vacuum and there's only a few particles in every cubic yard, that heat is maybe detectable by a thermometer, but to you or I, it would still seem incredibly cold. So that termination shock, this line here, it changes because the sun is moving through the galaxy. So in its direction of motion, that bubble might be closer than up here, right? Or back here. This bubble, you can kind of visualize it, well, a little bit. But you can imagine that this is the narrowest part of that bubble. So for Voyager 2, which was headed out kind of on this thinnest part of the heliosphere, it hit that termination shock at about 84 astronomical units, or 84 times the distance between the Earth and the sun. So by that scale, Earth would basically be inside the sun's lips. Voyager 1 took a different path out of the solar system. And so where it hit that the termination shock, it was actually a greater distance to the sun. It was about 94 astronomical units, or 94 times the distance of Earth and the sun. And Voyager has actually passed into interstellar space, which is defined as being outside of the influence of the solar wind. And that is about 122 astronomical units. So that'd be about here, or about 11 billion miles. However, as far away as the Voyagers are, they haven't yet reached the Oort cloud. So they may be outside of the heliosphere. They may be in what's called interstellar space. But this region is full of objects that are still orbiting the sun. So really, the space is interstellar. The cosmic rays here are more powerful than the solar rays. But we're still in the solar system. So that same distance that the Voyagers traveled in almost 40 years, that would take about 17 hours to travel that distance at the speed of light. And at the speed of sound, it would be 1,600 years. So if you could hear the sun, it would be much quieter than a rock concert this far out. But that you would be hearing sounds from explosions that happened on the sun back when the Roman Empire was still doing pretty good. And if you started in a car from the sun, it would take you 21,000 years to drive to the edge of the solar system, or at least to the Heliopause, this region right here. Walking, I would not want to walk this distance. 65 billion Manhattan blocks. And also closer to the sun, because the force of gravity, it gets stronger the closer you get. So those first billion blocks would be incredibly difficult. By the time you got out here, you could probably be, moving in leaps and bounds. But that's why you don't move at walking speed through space. You want to get through that really heavy stuff as fast as possible. But if you can imagine walking 65 billion Manhattan blocks, I can't. What I can imagine is the sun to the heliopause, that interface between the solar wind and the cosmic wind, or the local fluff, the cosmic dust. It's about 9.8 trillion Seths. So if you had almost 10 trillion of me laid end to end, we would stretch from the sun. That guy would have warm toes. All the way out to the heliopause, that guy would have a cold head. Actually, his head would be heated up by the particle interactions in the heliopause. How did Voyager know it was at the heliopause? That's a good question. It actually had a thermometer that detected a spike in temperature, which in a vacuum like that is measured by the kinetic energy, or the speed of the particles that Voyager slams into. Excuse me, sorry. All right, so I've got a little video for you here.
If you could drive around the entire planet, it would take more than 16 days of non-stop driving at highway speed.
16 days, I said 17, close.
Some of the planets in our solar system, it's pretty small. We often see planets displayed as similar in size, like this, to make details on smaller planets easier to see. In reality, the size of planets compared to each other looks more like this. Even though this shows the sizes of planets accurately, they aren't that close together. Because of the great distances between planets and the planet's relatively small sizes compared to those distances, it's practically impossible to create a visual representation on a screen or the page of a book that realistically represents the sizes of the planets and the distances between them. As a result, the best we can usually do is show the accurate sizes of the planets or the accurate distances between them.
Oh, it's hard to hear? Okay.
Remember, they aren't really planets. In space, the planets' positions are constantly changing as they revolve around the sun.
Sorry, I can play it again if we need.
You know, Seth, is that something we can send to people after
Oh, absolutely. Yeah.
with our resources? Maybe we can send them the link to that video.
Yeah. Yeah. In fact, I can probably just pop it into the chat here in a second. Sorry about that.
That's
You know,
okay.
the risk of setting your audio devices, you never know what it won't accept. Here we go. Can click right out of that. Ta-da. Moving on. And there we go. That concludes the presentation. But of course, I'm happy to take any questions that you may have.
Great.
Oh, thank you. I want to know more about the rocket. I appreciate it. Yeah, I'm really fortunate to be a part of the team. I can't really talk about it too much here just because I'm wearing my NASA volunteer hat, and I have to be careful. You know, I don't want to give the impression that NASA is endorsing, you know, my day job or anything like that. So sorry. I hope folks will understand. You know, I can acknowledge the material fact that I work for Blue Shift, but I can't say too much more here this evening. Oh, you're very welcome.
Great. Well, we will definitely send people that link, Seth, and we'll also send a link to the resources that the library has, so that people
terrific.
know that they can borrow our telescope. Mrs. C has an amazing collection of books. We've got star charts and all kinds of things. So there's all kinds of resources that we can send to people. And we will have a recording of tonight's program. So we can definitely send that to people too.
Excellent. Yeah, where's Lucy, can you help me remember where the astronomy page is here for the library? Oh, yep. No, I don't need Astronomy for Dummies. Actually, I probably could read Astronomy for Dummies. That's a good series. How do I navigate to that page there?
Do you see it? Let me get onto our website and I can.
All right.
I can share it.
Yeah, terrific. Here we go. Here we go. This is it, the monthly evening sky map. So if folks want to go outside and take a look at the night sky, it should look pretty much like what we saw in the present, you know, in the simulation earlier this evening. But another resource that you can use just off of Scarborough Public Library is to go to the monthly evening sky map, and you can print this thing out.
Yeah. And let's see. So on our Borrow the Telescope page, there are all kinds of great links, and those links will take you to lots of resources in the collection.
Oh, that's weird. I'm on here. This is my this is me. Ha! Oh, that's terrific. Okay.
So we've got a question about how did you become a NASA ambassador? That's a great question.
What a story. So for a while I had a radio show actually, and I wound up interviewing the CEO of Blue Shift, and it turns out he was interviewing me too. So before I know it, I have a job there, and I had to step away from the radio show. But the radio show continued on under a new name, and it's still going strong. All the other panelists are there. But while I was part of that radio show, we became the first public radio show, or technically community radio, but it's part of the larger public radio effort. But we became the first nonprofit radio show to join the NASA Museum Alliance. And as a result, we got access to curated content from NASA about its ongoing missions, which is all kind of research that I would have had to have done on my own in preparation for the show. And so it was terrific in terms of saving us prep time. And if we got a listener question about a recent mission development or something like that, almost every single time we would just go straight to the monthly email, and 2 clicks or less, some terrific resource to use on the show, which was really just amazing. And if you work for a science museum, or if you're an educator in STEM, NASA has a number of programs through the Science Mission Directorate to help make sure that you have access to really, really good STEM content. Anyway, as a result of joining that program, I met someone through the NASA Alliance who worked at the Museum Alliance, who encouraged me to apply to become a solar system ambassador, because he noticed that I really like talking about space. And so it seemed like a natural fit to him. And we'd actually interviewed solar system ambassadors on the show before, so I knew a little bit about the program. And I applied, and I explained that basically I already talk about space and NASA and all of its missions. And wouldn't it be really nice if the government gave me a badge? Hang on here, let me get my badge. To go do it. And so anyway, they must have thought it was a decent idea, because they let me in. I have the badge. See, I have a badge that says I'm good at talking about space. And so I applied, and a couple months later I heard back, and I've been doing these volunteer public speaking engagements ever since. And I'm very grateful to it, because otherwise I would just be that weird guy talking about space because he thought it was cool. And now I get to be part of a program full of people who talk about space because they think it's cool.
Well, thank you for talking about space to the Scarborough Library community. It was really, really nice to get a chance to hear you tonight, and was wonderful to hear you talking about Mars last night. And we're excited because, we call you our night sky tour guide, our Scarborough Public Library night sky tour guide. So you've taught us all a lot, Seth, and we're really grateful. Thank you for talking with us tonight.
Absolutely, absolutely. My pleasure. If you have any space questions down the road, you can reach out to me at this email address, and I will be happy to answer just as soon as I can. You can also find me as the Final Frontiersman on Facebook, Instagram, and Twitter, and I do check those inboxes regularly, and I would be happy to come back any month and discuss highlights in the night sky.
Awesome. I hope everybody's inspired to go take a look and see what's happening out there tonight.
Yes, please do. You never know exactly what you're going to see, which is funny, because the stars, they don't really look too dynamic, but there's always something interesting happening up there.
Awesome. Far out.
Yep.
All right, so we'll let everybody get going with their evening, and as you are fond of saying, Seth, over and out.
Over and out.
Take care, everybody.